Okay, so welcome to the next unit on the module on addressing mode, instruction set and execution flow. So, till now we have covered 5 units of the module in which we are discussing basically the basic architecture of the central processing units, how it is interfaced with the memory, then what are basic instructions are and how instructions is executed. Then we have also seen different format of instructions, and then we have seen how instructions basically can be clustered together based on their formats. Now, today we are going to focus on the next unit, which is actually very important in this part, which is called the addressing modes. That is, in other words, or in a name and language, what happens that all instructions, as we have discussed in the previous units, they require an opcode that which tells what it has to do, and of course you require the operands. So, how the operands are present in the instructions will be actually referred to as the addressing modes. Like for example, some instruction may have the data to be operated on in the instruction itself, like add 5. Then you can call it as an immediate instruction mode, but sometimes we may have the instructions where the data is deeply embedded in a very indirect manner. Like for example, the address of the data may be available in an instruction, which is something called a memory indirect. That is, there are different spectrum in which the data is present in an instruction. So, in this unit we are going to discuss in detail what are the different addressing modes. So, as we are dealing the whole course in a very pedagogical manner, so the unit summary will talk about different instruction modes. So, the first one which we are going to see is the immediate addressing. So, immediate addressing means the instruction itself will have the data. Then there is something called direct addressing, means the instruction will not have the operand itself, but it will be pointing to a memory address where the data will be present. Already we have seen in the few previous units that if you want to keep a very accurate or a data whose accuracy is high, it requires a large number of bits to be represented. So, if you want to do it as an immediate format, then the instruction size will become larger. To avoid that, we go for direct addressing, that we give the address of the memory where the data is present, and in fact the data can be accessed from there. Then there is something called indirect addressing. The details and advantages and disadvantages we will see as we will go along the unit. So, what is the indirect addressing? In this case, the data is not present in the address which is mentioned in the instruction. It is an indirect way of referring, that is the one hop reference. The instruction will have the reference to a memory, and in that memory location there will be another address which will be pointing to the exact data in the memory. We will later see that it allows you to expand the memory space or the size of the data to be represented. Then there is something called, we will see there is something called register addressing. So, register addressing is very similar to direct addressing, but in that case the only difference is the address refers to a register than a main memory. In this case, there are, as I told you, there are different variations in where the data is present. So, in register addressing what we do, instead of saying that the memory is or the data is located in so and so memory location, we will tell the data is present in such and such register. So, as the number of registers are small in number, so the data or the space in the instruction required for such type of addressing will be lower, as well as the access to data will be faster, because you need not go to the memory, you can directly get it from some other register. But again, the trade off is the number of registers are small, so you cannot have a large number of data present in this addressing mode. We have seen direct, indirect, then we have seen register. Similarly, there can be register indirect. So, register indirect is very similar to normal indirect, but in this case the address refers to a register rather than a memory location. So, what happens in indirect addressing? In the instruction you tell that this is the memory location where the data is present, but indirect means you tell the memory location, in that memory location again there will be a redirection to the exact data. But in case of register indirect, you are not going to refer to any memory location, rather you are going to use a register to do the indirection. And the next very important is something called a displacement addressing. This is slightly different from all others we have studied. In displacement addressing, basically there are two parts of the address. One part is exactly fixed, which is mentioned in the register in the instruction, and there is another part actually which says to whose contents are basically can be modified. It is similarly something like that. Say maybe we have a opcode and two parts of the address. One part is fixed, and the other parts actually can be modified, or it can be in fact they are added, and you can play on with this the variable addressing part, so that you can go for a wide spectrum of addressing like looping, or you can go for a displacement, that is you start from 0, then you put a buffer or you put a displacement to that, then you can move some 10x, start from 10x plus the current addressing. So, in fact, you can understand in a we will see in details when you are going into the module, but displacement means there are two components of an address, they are added to find out the effective address, and one of them is modified so that, or you can go as you, for example, you want to implement a loop. So, one part of the address can be changed or incremented and it is added to the other. So, you can get lot of displacement, you can go in a loop in that manner. So, displacement addressing is slightly different from all the others we have discussed till now. So, all others are basically kind of a static way, and here actually it is something like which is updated. So, you can go for a shift, you can go for a loop, etc. And the most common displacement addressing are relative addressing, base register addressing and index register addressing. So, that we will see, means based on the register in which you will be trying to do all this displacement, the names have been given. And then finally, we will see stack addressing. So, it is very simple, we have already discussed in the previous unit. In case of stack addressing, the off code or the instruction will not have anything basically rather than the only the off code, and all the data will be present in a stack. The top two elements or the top one element of the stack will be used to do the operation. And then what are the objective of this unit? The objective of this unit is first knowledge, you will be able to state different type of addressing modes. Then next is an application objective, you will be able to demonstrate the use of different addressing modes, that when it is better, which one has a trade off, which is faster, which is slower, which takes a larger space in the memory and so forth. And then finally analyze, then you will be analyze the advantages of different addressing modes, in particular the displacement addressing mode, because all other addressing mode, as I was telling, is some kind of a static, either the data is present in the instruction or the instruction has a memory reference where the data is there. But in case of the displacement, you add, you increment and all those, some kind of dynamism is present. So, this one we will be able to analyze that what are the advantages of such a kind of a addressing mode. Now, this was about the basic objective of the modules, the summary of the modules. Now, we are going to start the unit and we are going to look at real concrete examples and more in a more elaborate and a pictorial representation what are these type of addressing modes are. So, the first one, as I was telling you, was the immediate addressing mode. Immediate addressing mode means in the same instruction you will have the opcode as well as the data will be present over here. So, whenever this instruction will be fetched from the memory, you need not have to fetch any other stuff or any other memory location or any other register to get the operand. The operand is present in the memory location itself. Then the next but the problem here is that, as I told you, if your data is to be more precise, that you require more bandwidth representation, then this is not going to be a very handy kind of a addressing mode, because the size of the instruction is has to be then made 2 words, 3 words, which is not actually very fast to be implemented. Then what is another way of doing it? Then what you can do, then you can say this is called the direct mode of addressing, in which is the opcode, and here you will refer to a memory location, and we know that this can be quite, this is the width of the memory location. So, you have to just tell that which memory location the data will be present. So, there is a direct way of addressing. So, if you say opcode something at 32, it means the data is available in the 32th memory location, but in this case there is a memory operation required. But in fact, as you can see, obviously you can have a more wider space to do your operation, because in a general instruction format there will be an opcode, there is not only a one operand, there can be multiple operands. So, I mean you have to divide this space into multiple spaces. So, you will have a very less space for each operand, but if you refer to a memory location, then it will be just the address of the memory location and the data can be quite wide, or you can have a more precise data in that manner. So, this is called the direct mode of addressing. Then there is something called indirect mode of addressing. So, indirect mode of addressing is very similar to direct mode. In direct mode, what we have seen, that this one will refer to a memory location where the data will be present. But in this case what happens, the data will not be present over here, rather it will refer to another memory location where the data will be present. So, in this case, to get a data, you will have to have two memory addressing. So, first you have to address the first location, which will tell you the location of the data which is available in the, that means the data is available actually in this memory location. So, first one you will have, the instruction will tell you which memory location to address, which has the address. The memory address of the data is not directly present in the instruction itself, which was the case in the direct addressing. In this case, it will tell the address which will refer to a memory address, which will absolutely have the address of the location of the data in this and not here. So, this is actually the address and not here. So, there are two memory addresses required to get a data, but what is the advantage? As I told you, generally in a opcode, there is a number of operands present in an instruction. So, this is not quite large. So, what happens actually? So, in fact, I mean if the memory size is quite large, so you may not be able to put the whole full bandwidth of the or full range of the memory cannot be encoded in the small space. For example, if you require FF, so if the memory has 00 to FF number of locations, so 4 into 4. So, it is FF, then actually you require 16 bits to represent the memory location. But in fact, if you understand that it is divided into 4 number of operands, so you may not have the space to represent a 16 bit operand over here, that is the memory address of this. So, in this case we can restrict that my data part will be a smaller part of the memory, maybe I can say that F00 FF will be limited to the range of the data. So, in this case the 00 will be explicitly given, it is implicit, and this only FF has to be kept over here. So, I am actually making the size of the opcode, size of the operand, means address of the operand in the memory smaller. Then you will apply FF, 00 will be explicit. So, you can go over there, but that is one way of doing it. The other way of doing is in that case now you have we will refer to this one. Now you need to actually address the full memory for that, because memory the data can be anywhere in the memory. So, it may refer to this one, but the exact but to access the full memory you require to access the 16 bit, that is 444 for the 16 bit address space of the memory. Now, where it will be present, the exact location of the data will be the data may be available in say F9. So, data may be present over here. So, what it will do? So, you are referring only FF, because the exact location, that is F9 is actually present over here. So, this one is having the value of F9 where exactly the data is present, and in fact that F9 will actually take 16 bits to be represented. That much space I do not want to keep in the instruction. So, but in the instruction I give the only say value FF, that means it refers to the first the 00 is explicit. So, it just refers to the this memory location, and in this memory location I have the, because this is much is quite wide compared to this smaller space in the memory. So, now you can access the whole range of the memories. So, that is one advantage of the indirect addressing mode. There are several others, like we will see, then actually we require an indirect addressing mode for implementing or accessing arrays and all those things. But as we have not gone into that much of details in the course as of now, so for time being this understanding is enough, that to get a more full range of the memory access, such an addressing mode is useful. Then next we are going to, this was all about the direct, indirect and immediate addressing mode. But there is another way of doing it, that is instead of referring to the memory locations, the data can also be present in the registers, because register access is more faster, it is inside the CPU itself, and then other advantages are there regarding speed, etc. But again, what is the disadvantage? The disadvantage is the number of registers are smaller in number. So, if you have more number of data, that cannot be accommodated in a register, but it can be accommodated in a memory. But for certain access, like you want to store some intermediate results, where you want or the data which has to be fetched more frequently, it can be temporarily stored in registers. So, what is a register direct addressing mode? The opcode will be there and there will be address of the register. In this case, actually instead of referring to the memory, you are going to refer to register. In fact, registers, if there is 32 number of registers, or in fact if there is 16 number of registers, then you require just a 4-bit representation to represent any of the 16 registers. If there are 32 registers, you just require a 5 bits for the address of the register. Say for example, if you write some add and then you write say 32, that means what? That is 2 to the power 5, that is 1 1 1 1. Okay, then in that case you will be referring to the 32th register, that is last register if you are having a 32 number of registers. So, you can see that the size of the instruction will be smaller, and because the number of registers are less in number. So, register direct means it is just like a direct addressing mode. The opcode will have the address of the data, but the data is present in a register and not in a memory. Then same thing also applies for register indirect, just like a indirect addressing mode, there is also indirect register addressing mode. Like for example, in the direct addressing of register, so the opcode refers to a register and your data is present over the register in this register, but in this case it is an indirect one. So, your opcode is there, you refer to a register and the register actually refers to part in the main memory where the data is present. So, this is register indirect. What was the normal indirect mode or the general indirect mode? General indirect mode means from the opcode you are actually pointing to one memory location which contains the location of another memory location which actually has the data. In case of register indirect, you are giving the address of a register, the data is not in the register, but the register is pointing to another memory location where the data is present. And the advantages I told you, that is if you are going for indirect addressing mode, you can access the full range of the memory because number of registers are small. So, if you compare to the general indirect addressing and register indirect addressing. General indirect addressing means you will first refer to one memory location here and from that you are going to be redirected here. So, you require two main memory access. But in case of a register indirect, the first you refer to a register and then you refer to a memory. So, in this case this is one register access and one main memory access. So, this is a more faster way of getting the operand because register accesses are more faster compared to a memory access. So, in this case there is a one memory access and one register access. So, it is more faster than your normal indirect mode where there is two memory access. So, that way there is advantage and disadvantage. Disadvantage is registers are less in number, so you cannot use it very often, while main memory is larger in size. So, you can have more frequent such type of indirect addressing mode. Okay. So, now let us go to some concrete examples. That is, let us take a very simple memory which has location from 0 to 7 and the content are 2, 49, 5, 20, 12, that is this way. And let us assume that we have a register whose content is 3. So, let us write an instruction load immediate 20, that is maybe the off code can be something like LDI. Generally here I have discussed in a more linguistic manner, but we always have a mnemonic for that. So, it may be LDI, that is load immediate, or you can put, sometimes person may call it load indirect also. So, you can also have the word load immediate. It is up to you how you define your instruction set. So, it is load immediate 20. So, what does it happen as an immediate? So, in that case the value of 20, binary 20 will be in the instruction itself. In immediate mode of instruction, you need not refer to any of the memory location, neither you have to refer to any other register other than the accumulator. So, it says load immediate 20. So, in this case what happens, the value of 20, that is 20 binary will be loaded into the accumulator. Load direct 30. This is a direct addressing mode. So, what is the direct addressing mode? Direct addressing mode means this 30 actually refers to the memory location 3 where the data is present in the memory location 3. So, direct. So, load accumulator 3, that means to the accumulator you load the data which is present in memory location 3, that is 20. So, the 20 will be stored in the accumulator. One thing you remember, register R2 has the value of 3. R2 has the value of 3, that you have to remember. Then load indirect 5. Now, this is interesting. Load indirect 5 means accumulator will be loaded with something which is present in memory location 5. Memory location 5 has value 1. Now, it is an indirect. So, 1 is not the data. The data is actually present in memory location 1. So, what is memory location 1 present? That is 49. So, the 49 will be stored in your accumulator. That is load indirect 5, 1 is the content. This is nothing, this is not the data or the operand. Basically, it is the address of the memory where actually the operand is present or the data is present, that is 49. Then load register direct 2. So, in this case as I told you, what it says, it is a direct instruction, but instead of referring to a memory, it is referring to register. It is saying that load register direct 2, that is you load to the accumulator what is available in register number 2. So, as I told you, our assumption was register 2 has the value 3, so it is loaded into the register. Next is as this is normally indirect, so this is called register indirect 2. So, register indirect 2 means, so register 2 has a value of 3. So, now is the indirect mode of addressing. So, 3 is not the data. Basically, you have to access memory location 3 because 3 is present over register 2 and the content is 20. So, 20 will be loaded over here. Same thing like load indirect, but in case of register indirect, we first refer to register 2. Register 2 has the value 3, 3 is not the data over here, we have to look at the memory location, 3 is there, where the content of 20 is there, the 20 will go to the accumulator. So, this is an example of register indirect addressing. Then as I told you, So, all these were somehow what I called you is something like a static kind of an addressing. So, you refer there, then you go for indirection and you get the value. But whenever you talk about displacement basically you will find that there are two components of addresses which will be used together to get the effective one. So, what is the displacement mode? It says it has two address fields. One contains an explicit address of main memory, so that is A, it has some explicit value, and the other address fields refer to a register whose content something, say R, it refers to some memory R, that is one of this component refers to the memory, another R corresponds to a register. So, it has two components basically, one is for the memory and one is for the register. For obtaining the exact value that where the operand will be present, these two are actually added. So, for example, if it says the memory location 3 and the value of this may be 2 for example in the register, then what is actually happening? So, it is referring to register 4 and register 4 has the value 2. Then this 2 and 3 will be added, together you are going to get the value 5 and 5 is the place where actually the data will be present. So, there are a lot of advantages over this, means compared to the other ones, there are a lot of applicability of this one. First is if you think of loops, then actually it will go say I want to access 10 memory locations one after the another. So, it will first start with say I can make this content as 0, then it will start with 3. This memory location is 3. So, it will start with 3, then I increase 1, then it will go for 4, 5, 6, 7, 8, 9, 10. So, I can just change the value of the register by 1, 1, 1, 1 and you can continuously access first location, second location, third location and so forth. Similarly, for an array, if the data are present in a contiguous location in the memory, so you can access different elements of an array by such kind of a displacement mode. There is something called relocatable loader. In that case, what happens? Say you load the whole code, say for example a program counter etc. starting from 100, then the program counter jumps because of a jump instruction. So, in this case as we will see later, you can change the value of the register and you can give the value of say initially my program counter was 10, then you jump to 20. So, you make this location counter as say 10 or something like that. So, there will be a jump of plus 10. So, such type of lot of cases where some dynamism is required, so where you require the displacement of the addressing like jump, increment by 1 in case of loop, such kind of addressings are required. But in this case you have to know that difference from all others are that you add the two values of the components, that one is the memory location content and another is some register content, and together you will get the value and you can modify with the register content by 1, 5 whatever one you want as displacement they will be added and the effective address will be calculated. So, there are different variations of displacement addressing. In fact, the variations all starts based on what register you are accessing for this. The second part is more or less constant, that is constant in the sense that it refers to a memory location in the main memory. But what register you are using it for and what is the purpose will define the different types of displacement addressing. Like first is the relative addressing. So, it is also called program counter relative addressing. In this case, the register actually contains the PC. Say if this one is the register addressing, if it is a relative addressing, so is actually where the displacement is present is the program counter. So, generally in this case, so if you see here we get the operand by displacing a number of locations from the current location pointed by the PC. That means, in this case the effective location is obtained by the location of the PC, content of the PC, that is where the PC is pointing, you add it to A and then you get the displacement where you have to start. Generally jump instructions and several other similar kind of things are addressed, or when you want to go for such type of such mode of operations you require, like there is a jump instruction etc., then you can use this type of addressing mode. Because in this case the program counter actually has the displacement value, there you can load different values and the jump will actually happen based on that. There is something called base register addressing. So, instead of the program counter, if the reference registers contain the main memory address and the address field contains a displacement, so if the name of the register, if I call it as a base register instead of the program counter, if it is a base register, we call it as a base register addressing mode. And if the address field there are three types of registers basically. So, one is actually called the relative addressing if the register is a program counter. If it is a base register, then actually for the displacement we will call a base register addressing mode, and index register addressing mode basically is now a general purpose register. It is same as relative addressing, but with a different register, that is a general purpose register. So, instead of base register or instead of program counter, if you are using R1, R2, R3, R4, which is a general purpose register, we will call it as a index addressing. Index register addressing is generally used for loops. Like for example, I equal to j, I equal to 1 to 10, then do something. So, that if I refer I to a register, then it will actually I call it the index register addressing, because I will map I to a general purpose register like an array. If there is an array and I index it with j, so 0th element, 1 element, 2 element, 3rd element and so forth. So, I call it as the index of the array. So, that index of the array means which will be incremented, and I want to address first memory location, second memory location, third memory location and so forth corresponding to that array. So, that index of the array is basically mapped to a general purpose register whose value I will be incrementing by 1, and then from which memory location the array starts, that will be the explicit part of the addressing, like this one. So, A means it will be the starting point of the array, and this will be your index register which will have the initial value 0, then you go for 1, 2, 3, 4, 5, 6, then you access the entire array. So, if this register is general purpose, then we call it index. If it is a base register, then it is base register displacement addressing. If it is the program counter, we call it as a relative addressing. The functionality is more or less similar. That is, there is a memory location and you have to address 1, 2, 3, 4, 5, 6, or you have to jump from memory location x to x plus 5. So, this type of addressing is displacement addressing is used, but based on the address or based on the register which is used for that purpose, there are different types. So, again it is better, a lot of theory we have discussed. So, it is better to take some concrete examples for this addressing mode, that is displacement addressing mode, to make the things clear. So, first I am taking a relative addressing mode. Relative addressing mode means that the program counter is directly involved. So, you are writing load 0 1 1 and then this is the value. So, as you are all assuming that there is an accumulator default instruction. So, it says that the register R3, because this is the register R3 and the address is 15. So, that means whatever is the content in R3, the address 15, that is, this is your addressing to the main memory, this is location to the memory. Then is added to the content of the program counter. So, base register. So, whatever will be the is an immediate addressing relative addressing mode. So, PC is default one of the register, and in this case what it is saying, the register R3, that is register R3 is the register, the content of this is 15, will be added, this 15 will be added to the content of the PC, whatever the PC will be have the value, and that content, that is 15th memory location plus the content of PC, will that data will be taken and loaded into the register number 3. If the memory location has, so in this example they are assuming that the program counter is 1. So, if the program counter is 1, then 15 plus 1 will be the 16, and whatever is present in the 16th memory location will be added, will be loaded to register R3. So, what happens? 15 is the memory location, main memory location, program counter is 1, 15 plus 1 is 16, 16th memory location, whatever will be the data. So, if it says PC has the value 1, 10 is loaded in the accumulator, sorry 10 is accumulated register 3, because they are assuming that the memory location 16, address 16 has the value of 10. So, program counter was 1, this explicit addressing was pointing at 5, so we add it and load the value of 10, that is the operand, to register R3. So, if it is a accumulator type of addressing, then what we can do, let us make it a very, it will be more simpler. So, it can be something like, we can say write load, we can remove this. So, an accumulator based addressing. So, in this case it will say load, that is load relative. So, relative addressing load 15. So, what it will mean, that whatever is in the program counter content, in this case is assuming to be 1, you add it with 15, then memory location is becoming 16, 16th memory location is having the value of 10, this 10 you load it to the accumulator. But in this case that will go to accumulator, but in this example they are not taking the example of an accumulator direct machine, they are taking the value of R3. So, the content will be loaded to the accumulator, sorry, content will be loaded to register R3. So, whether it is a register R3 or whether it is loaded to the accumulator, that does not depend on the, that does not has anything to do with the addressing mode. The addressing mode basically in this case is a displacement addressing mode, take the value of PC, add to 15 and load at some place. In this case it is register 3, if I drop this and assume it to be an accumulator based accumulator based instruction. So, it will load it to the accumulator. Now, let us in this example we are not considering that it is directly loading to the accumulator, we are all considering that the destination is register R3. So, if you look at it, it is a base register addressing. So, in this case, as I told you that here in the last case we have not mentioned anything here, it was default was the PC, but in this case as I told you, instead of using a instead of using a PC, if I am using a very special register, in this case they are assuming that the R5 is a base register. So, that content will be added to 15 and you will get the effective value of the memory location where the operand is present. So, the content of R5 is added to 15 to get the effective address and the content is loaded into R3. So, in this case if we assume that just like program counter, if this register R5, that is the base register, has a value of 1, so it will be again 1 plus 15 will be 16, 10 is there in the 16th memory location, it will go and load into R3. Say for example, but if I have the base register value of 2, so it will be 15 plus 2 17, so whatever will be available in the memory location 17 will be loaded to register R3. So, only difference in between these two, that one is a program counter and in this case there is a very special register which is a base register and you are doing the same functionality. But as I told you, program counter is a very special rule, it always points to the present memory location to be executed. After that it goes to the next instruction. If there is a jump instruction, it goes to the jump location. So, in that case this type of instructions are extremely useful because there is something called relative loading. So, we always when you are say generating a code in the offline of just after compilation, then we assume that the code starts from memory location 0, but due to non availability of the 0th memory location to be loaded and executed, it sometimes get loaded at starting from 100th memory location. So, the program counter will be starting from 100. So, in this case program counter value 0 will be added to 100, which is actually this value, you can make it 100 because your code could load from memory location 100 and it could not load from memory location 0 because it was not available. So, you can all find the details of such type of concrete examples in the course on assembler, linker and loader, which is actually called relative addressing. So, in this case we are always assume that the location or the execution starts from 0, all the addresses of the assembly language code are assumed from 0, but then when it has to be executed it may not start from 0th location, it may start, we have a displacement. So, in this case this value we can give that displacement, say starting from 100, so you put 100 over there, so program counter will start from 0, so it will be 0 plus 100, so effectively whole thing is displaced below by 100 memory location and the execution happens. So, that is a very that is the use for this type of addressing when we are going for some kind of a relative addressing or relative loading kind of a thing. Base register means instead of the program counter, the value of this can be or this program counter is not used for that, you have a base register in which you can do some kind of a displacement. Then the last one is the index register. As I told you, index register, that is this one, sorry. The index register, this one is a general purpose register. This is not a base register, this is not a program counter. You can have, it can be R1, R5, R10, R12, which is a general purpose register. So, in this case the instruction is add 101, that is register 5, this is register 1 and some memory location is 1, that is the stuff. So, here R1 is the index register, it can be any general purpose register. In this case what they are doing, they are using it as a loop. So, as I told you, one of the most important utility of index addressing is loops basically. So, here R1 is the index of some loop. So, it is saying that whatever available content of R1 you add to 1. So, that will be the effective memory location. In this case if the R1 is 0, so the effective memory location is 0 plus 1. So, the first memory location, the contents of the first memory location will be added to whatever was the content at R5 and it will be stored back over here. So, R5 is equal to R5 plus content of R1, that is the memory location. So, what is the memory location over here? So, let me just write it. So, what is this effectively trying to do? So, in this case register R5 will be R5 plus what is the content of the memory location. How can you find out? Means whatever is R1 will be added to the content of the memory location. How the memory location is calculated? It is content of R1 plus 1. So, I add value of 1 and I add what is the content of R1 that will be the effective memory location. I will get the operand from there, add to R5 content and store in the R5 itself. So, initially they are assuming that R1 is having the value of 1 and R5 has the value of 0, that is R5 is reset. So, it is something like S equal to S plus I. So, S is reset and the I is going to be incremented. In fact, what is I? So, in fact, it is something like S equal to S plus AI. So, A is the array and I is your instruction. So, R is basically nothing but in this case your R1 and S is nothing but in this case your R5. Okay. So, now see they are saying that the initial content of R1 is 1 and R1 is 1, R1 is 1, this R1 is 1 and R5 is 0, that is reset and this is 1. So, initially the elements of the array may be starting from 1. So, arrays are location of the array are starting from memory location 1, 2, 3, 4, 5, 6 and this initially has the value of 0 reset and R1 has the value of 1. So, what will happen? The instruction takes the address 1 and adds to the content of R1. So, the content of R1 and R2 both have 0. So, initially both of them has 0 value. So, that is this 1 will be added to the content of R1. So, R1 is having a value 0, 0 plus 1 is 1. So, effective address is 1 and it will address the first content of the memory location. So, the memory location is something like this. So, 0 that is garbage, 1 there is some data, 2 there is some data and so forth. So, initially your both R5 and R1 are reset. So, generally it has the value of 0, this also has the value of 0. So, 0 plus 1 is 1. So, you are going to address this value. So, whatever will be the content will be added with 0, that is the content of R5 and it will be stored over here. Next what you will do, you will increment the value of the register number R1. So, R1 will be contents of 1 will be added to the content of R5. So, that will be done. Then next, that is actually what I have told you, whatever is present over here will be added to the contents of R5 which is now 0. So, it will be 0 plus the content of this one which is nothing but this one and it will be stored at R5. Next, the content of R1 is incremented. So, this one will now have the value of 1. So, 1 plus 1 will be 2, now we will be pointing to this memory location, that will be again added with the content of 5 and stored back. So, it is something happening like S equal to S plus AI, where A is an array and I is the index. So, this index is actually keeping on incrementing by 1, 2, 3, 4, 5, 6 and it is and that continuously first array location, second array value, third array value, fourth array value you are getting and storing it that one. So, that is what is a very simple example of an indirect index addressing mode, which is again a displacement addressing mode, but this index register is our own defined or user available register, which is R1 in this case. In the other way it can be any register which can be used by a programmer. Okay. So, now basically now we are going to see some more examples which will give you a more in depth idea of how basically addressing mode happens, where the values are located, etc. Because in most of the cases, as I was saying, that the instruction is basically opcode and some operand or some addresses, but sometimes the size of the instruction cannot be such nice or the length of the the width of the memory cannot be so good that it will hold the whole instruction in one word. There can be in multiple words. That means the opcode will be one place and some part of the operand will be there in the word and the space is exhausted. The remaining part of the instruction will go to the next memory location. So, taken the two memory location together, you can have a instruction. So, that is called multiple word instruction. So, now we have to go look at such complexities. So, we are considering a CPU with 8-bit data bus and 16-bit address bus. So, it is very simple. It is something like this is 8 bits and the whole space is 2 to the power 16. Then some other assumptions here we are taking. So, what is the assumption? The first byte of the instruction is the opcode. So, what do you mean by that? So, in this case, as I told you, the instruction has some specific characteristics. That is the opcode, and then after that you can have lot of other modes like if it is immediate addressing, you have the data value, etc. So, when I say there is the opcode, so when I say that basically this is your opcode, so some part of the instruction is default taken by this one. So, in this case I am saying that the 8 bits. So, as I told you, the instruction basically has opcode and then some other places for operands. So, in this case I am assuming that the first byte is the instruction itself. That means, if it is a 8-bit word, so I am saying that the opcode takes the whole part of it. That is, because we are trying to discuss in this part, that is multiple word instructions. That is, this is your memory, this is your 8 bits, and in fact this part of code is taking the whole 8 bits together. So, then what will happen? Then the operands will be present in the other parts, because there is no space available to do that. So, for 2-byte instruction, the second byte instructions, because in this case there cannot be any single word instruction. Single word instruction, because one word actually in this case is 8 bits, and if you look at it, the whole 8 bits are taken by your opcode. So, obviously this 8 bits is the opcode, the next second bit can be some kind of an operand. So, for 2-byte instruction, the second byte instruction data, or it can be, if it is a direct addressing mode, so it will be reference of a memory register. For 3-byte instruction, the last two, basically these two will be your data, or it will be pointing out to some memory location, and this one will be your opcode. So, in fact, what it is showing, that if the, in this case the memory is 8 in length, and the means instruction size is larger, because the opcode is 8 bits, and then other bits are reserved for operands or data. So, the whole instruction has to be spread out into multiple memory locations, and in fact this is what basically happens in all cases. Very rarely you will find instructions which will fit into a single word. Then if it is a single word instruction, then life is very easy. First program counter 1, then program counter 2, then program counter 3, one instruction after another. But if there is multiple word instruction, then first one, if it is a 2-word instruction, then you jump to 3, then if it is a single word instruction, then you jump by 1. So, the movement of PC is non-regular, and it depends on the size of the instruction. So, we are assuming that the memory instructions are, for this present example, we are assuming that the instructions are stored in a memory location which is continuous, and it starts from 0770 hex. So, this is present pictorially. So, this is the first instruction is add immediate 75. So, that means I told you it is a 8-bit, as well as your data is also assumed to be 8 bits. Now, in this case I told you the whole memory size is only 8 bits. So, the instruction, this whole instruction together cannot fit into a single word. Add immediate ADI, that will fit in the first word, that is 7070 hex, and the next, that is your data, as is an immediate instruction, it will be available in the just immediate address, immediate word. So, in this case first your program counter will go over here, and when the instruction is executed, after that it has to go to the third memory location. It cannot be the +1, it will be +2, because in this case it is a 2-word instruction. If it is a 3-word, it will be +3. So, what happens? So, this is the case, the data is 75, add immediate means load the value of 75, add the value of accumulator with 75 and store back in the accumulator. So, this 75 is taken, it is added to the accumulator and written to the accumulator itself. So, this is the example of a immediate addressing mode, and how it is stored in 2 words, we have shown that. Next is add, this is a direct, that is, it is saying that this is your memory location. So, it is saying that add is the first gone, that is 8-bit is taken, then now in this case it is not an immediate addressing mode, it is a direct addressing mode. So, it is referring to a memory location. Memory location in this case is requiring 16 bits, that is first hex value, second hex digit, third and fourth. So, now obviously this 2 is 4 bits and 8 bits, and this 2 is 8 bits. 00 is 8 bits, that is 00000000. 7 means 0111, and 5 is 0101. So, 00 and 75. So, this is taking 8 bits and this is taking 8 bits. So, this will again occupy 1 word space in the memory. So, this is the opcode, then 00 is the LSB, and this one is the MSB of the address. So, it is stored over here. So, now add direct. So, 0075, that is 7500, it will be addressing. So, these 2 will be together addressing the memory location 7500 hex, content is 5, and it will be added to the accumulator content and stored back to the accumulator. So, now you can easily appreciate the fact, now as the data, memory location, everything is split over multiple words. So, the hardware is becoming more complex, because in this case I have to add these contents of 2 different memory locations side by side, then I have to give it to the address bus, then I can only get the value of 7500, and I can address that memory location, I can get the content 5. But if your instruction was quite big, maybe in this case 8 plus 8 plus 8, 16, 32, If this can be 32 bits, then program counter will be first here, then it will be +1, then it will be +1 and so forth, and then these two you can just take together and you can address this. That means you need not address two different memory locations to get the value of the effective address. But actually this is not, as I told you, this is not a very practical situation, because we cannot have such wide memory. Means in 32-bit memories are available, but as we are discussing in a much more scaled down tone. So for us basically this may be a quite large size, because nowadays when you are talking about 32-bit memories, then the memory size is becoming so high that 16 bits are not enough to represent the whole spectrum of memory, which can be in the levels of gigabytes. There are several other examples we are taking one by one. So in this case it is saying it is add immediate 0800, okay, and then it is add indirect, and in this case add and the bit is 8800. So the content of the main memory value will be present in 8088. So it will be, it's an indirect register. So what happened actually? So in this case it was all direct, but this is an indirect one. So in this case it is saying add indirect, the content of memory the operand is 0800 and it has to be stored with the, it will be means accumulator has to be added. So it is an indirect addressing mode. So whatever is the opcode is saying add something to the accumulator, but where I will get the operand is an indirect one, it is saying 0800. That means these two will be referring to a memory location, that is 08000. That is we will add it to the content of memory location 8000. But what is there? It is 8000. So the content here is 70. But as it is an indirect addressing mode, I cannot do that. Indirect addressing mode means here again I will get the, I have to again refer to this memory location to get the exact memory location where the data will be available. So it is pointing to 800. So this is the location. Now in this case it is mentioning as 70, because this location is again 8 bits. So but the whole memory size, the length means memory address space is 16 bits, but the width is 8 bit. So here the content is 70. So it is actually these two taken together is referring to this memory location 8000. So now it is having the value of 70. So the real content of the memory should be available in memory location number 70, but 70 is an incomplete address. Something more is required because the memory address space is 16 bits. But as this width is 8 bit, so the whole instruction, whole address cannot be placed over here. So by default I will again take the next value. I have to take both the values because this is 8 bits and I can only store half of the address here. So it is 70 FF. So basically the effective address is FF70, which is actually again a redirection from here to here, where actually the data is present, which is 5, which is added. So let me tell you. So what happens? Add immediate 8000. So that is what is the address of the indirect address of the data. So I am going over there. The content here is 70. So by indirect addressing, the content should be available in memory location number 70. But 70 cannot be a memory location address because the space is 16 bits and this space is only 8 bits. So I require 2 words to store the again address. So by default 8000 plus 1, these contiguous memory locations are taken. So 70 and FF. So FF and 70 are taken, which is this memory location, which is the exact location of the data which is available as 5. So in this way I go on calculation. So if you can understand that if more values or more number of operands or operand may be more precise or larger memory space has to be located, then your instructions start becoming multi-word instruction. So in this case it is a 16-bit memory. So you are requiring 2 words other than the opcode to get the address. If the address space is, memory space is slightly higher, say it is 32 bits, then you require 1, 2, 3, 4 memory locations to address the whole memory space. So higher memory space means in this case you will require more number of memory locations to do it. So it becomes a more number of multiple word memory. Then just we complete and go to other examples, let us take a very simple example of add x, which is the displacement addressing 50, 80. So in this case 50 is one part, 80 is another part. So as we all know that basically if you look at it, so 80, 50. So in this case add x, that is your displacement addressing, we are assuming that, and the content is 50 and 80. So basically, and there is an index register. So basically in this case it is a displacement addressing mode. The address is obtained by provided in the instruction with the value in the index register. So, in fact, actually it should be add x. I am just making a slight mistake. So, again basically maybe I can call it as R4, which is my basically the index register. Here I have forgot to mention it, it should be basically R4 or something like that. That add x R4 and then 5080. So, 5080 basically the instructions start from 70, the next two bits are this one. So, in this case 8050. So, this one will generate the address location of 8050 which is in the instruction, and the instruction is add x R4 8050 and R4 assuming that the content is 1, which is shown over here. So, you are adding it to, so it will become 8051, the content of 8051 is 5. So, you will add with the accumulator to get the value. It is a simple displacement addressing which I have told you. In this case I am explicitly referring R4, which is my index register, assuming the value of 1. So, the memory location in the instruction is basically add x R4, and in that the R4 is added with the content that is 8050, that is 8050 with 1, that is 8051, the content of 8051 is 1, sorry 8051 is 5, and you get the value. So, in this case the displacement has happened by 1 because the value of the index register is 1. Next, if I increment the value of index register by 2, so it will be accessing memory location number 8052, and we can keep on doing it. Then the last addressing mode, which is quite simple, used mainly in a stack machine. So, in a stack machine what happens, as I told you basically the simple example we have taken. So, let us assuming that there is a stack, over there and there is a pointer. So, the stack can go from anywhere because we generally get to access only a certain portion of the stack. So, there is something called a stack pointer, and then we can do such type of instruction like push, pop, add, sub. Push means you are here the number of instructions will be very limited. We have already discussed in some previous units, like you can push the values, you can pop the values, and when you want to do some kind of an operation, it will take the top 2 elements. So, some examples like push, pop, add, sub, some of the examples we will try to show. So, this is an empty stack, and then this is the stack pointer. Maybe say that we will start pointing from here, this is the top element, this is the whole stack available, and we will do some of the instruction which we have seen in the this question, that we will first push 15, then push 12, then 15, then we will add, and so on. So, this is the first scenario. Then we say that push 15. So, 15 will be pushed in the top position because it is an infinite stack, because this may be available to program 1, then the other part may be available to some other program, and so forth. Then it is saying push 12, so second 12 will be pushed, then we again say push 15, so the value of 15 has come. Next you see I will say add. So, what if you say add, what happens? It will take the top 2 elements, add it and put the value there itself. So, it is 15 plus 12 is 27. So, 27 is pushed back over there, and this is the stack pointer. Then I say sub, then what will happen? It will subtract these 2 values. So, it is 15, 27 minus 15, that is equal to 12. So, the subtraction will be done, the value of 12 will be present over here. Then I say again say push 20. So, the next value will be pushed on the top. Then the next instruction is push 12, again I push a 12 over there. It is a very simple operation. Stack machine is one of the most simplest computing that is available over here. Only thing is that it is more slower to do it, because in fact you have to do any 2 operation, you have to first push the values and then you have to operate on the last top 2 elements, and the answer will be pushed over here. Slightly slower way of implementation compared to a general computing, where you have lots of different modes of instructions, different type of instructions, etc. So, I have pushed 12, then they are saying multiply. So, if you multiply, it will take the top 2 elements and multiply, it will be 240. So, 240 will be there over, and then finally I say subtract. Some example, this will subtract these 2 values and the value will be put over here. There are just some examples that how basically a stack machine is implemented. Only 3 steps: push, pop and operate. Push means some elements will be pushed, pop means the top elements will be popped out to the memory buffer, and operation means you will operate the top 2 elements. So, if you look at this slide, they are discussed in details, like push 15, push 12 is done, and the top 2 elements are added, and then you subtract with 12, then again you push the 2 elements, and then again you multiply, and finally you will see that this is what is the expression that is actually computed. So, this stack mode of instruction execution is extremely simple compared to all others, but it is a more slower way of doing it. Okay? So, basically this brings us to the end of different addressing modes, which we have seen in a wide spectrum from immediate to as long as displacement with index displacement, program counter displacement, base displacement. So, there is a wide variety of instruction addressing modes available, and based on the requirement we choose any one of them. So, towards the end, as we have seen, let us take very simple examples, like explain with example different addressing modes. Already we have done, and it will basically satisfy your objective, like explain the discuss. If you consider these examples, that what explain with the examples different addressing modes, what is displacement and what it is required. So, if you look at the objectives, the questions we have shared, like other the two questions were what are the different type of addressing modes, what are the examples. So, basically it satisfies the objectives of state the different addressing modes, demonstrate the use of different addressing modes. The second question was, if you have referred to the question, it asks that what are the displacement modes and what it is, where it is useful, different type of examples. So, basically it will satisfy the objective of analysis of different type of advantages of different addressing modes. So, just now we have listened to different type of addressing modes like immediate addressing, then what are the other types of addressing modes which are indirect, then basically registered, and so many variations we have discussed. And now let us look at some simple questions and let us see how it satisfies the objectives we have targeted before starting this unit. So, explain with examples the different type of addressing modes like immediate, direct, indirect, so many we have already discussed. So, if you are able to, I think with this unit of the understanding this unit and with the several examples we have discussed, you will be able to solve this problem, and once solving this problem, of course, you will be able to demonstrate the use of different addressing modes, and also you will be able to state the knowledge of different addressing modes. That is, whenever you are going to explain somebody the different type of addressing modes basically and the advantages and disadvantages, you will be able to meet the objectives of stating the different type of addressing mode, demonstrating the different type of addressing modes with examples, and also analyzing the advantages and disadvantages of it. And already we have seen, apart from the normal instruction modes, addressing modes, there is something called displacement. That is, from the one part we can easily go to another path based on indexing, generating the effective address space based on one part of the instruction by adding it with the explicit addressing and so forth. So, if the second problem says that what are the displacement addressing modes, different types like index, base register, etc., and explaining with the examples and what are the advantages and disadvantages. Of course, this will be helping you to solve the objective on analyzes the advantages of displacement addressing modes compared to the other addressing modes like immediate, direct, and so forth. So, just by completing this unit, you will be able to state, demonstrate and analyze the advantages and disadvantages of different addressing modes, the cost, what you achieve, and how complicated is one addressing mode than the other, but what it gains. So, basically this brings us to the end of this unit, and next unit what we are going to see is that basically what are the instructions we have seen till now are mainly sequential, 1, 2, 3 and so forth, but in a program the basic logic comes if you are based on some condition, you do either this or you do either that. Without this, no program is complete, or in fact no program can be built without such a conditional logic. So, the next unit we will be focusing on conditional statements, flags, how a conditional code executes, that if it is true you do this and so forth. So, we will be next unit we will be looking at the flags and conditional instructions. Thank you.